Good afternoon, folks. My name is Venkatesh. I'll be the host for you today. On behalf of Skilling, I welcome everybody. For those of you engaging with Skilling for the first time, we are an engineering upskilling platform focused on advanced technologies across domains like mechanical, electrical, electronics, computer science, engineering, etc. This webinar is part of our enterprise business, which focuses on employee training and upskilling across industries, including automotive, consumer electronics, ITES, across various verticals. Today's webinar is on recent advancements in lithium-ion batteries. This is the 21st edition of our webinar for corporate professionals. Some pointers before we start the session. We welcome everybody to post their questions on the chat window. Mr. Vatsal will pick it up at any point of time. We'll also share a feedback form on the chat window. Please spare a minute to fill it up. We'll share the recording of the session to folks who have filled the feedback form. And about today's instructor, Mr. Vatsal, he's the program director for electric vehicles at Skilling. He brings over 16 years of rich industry experience from reputable firms like ABB India, Atom Energy Future, etc. His expertise spans across critical areas, including electric EV powertrains, lithium-ion battery technologies, charging stations, power electronics, motor drives, and solar power systems. We are excited to host everyone and hear from you, Mr. Vatsal sir. Over to you.
Yeah, thanks a lot, Venkat. I hope I'm loud and clear to everyone.
Yeah.
Thanks. So before we get started, I think Venkat already introduced me. I would like to spend some time in couple of more things about myself and Skilling. So I come up with total 16 years of experience, and I did my master's in electrical electronics and worked on various projects. So I am a practicing engineer. I made my hands dirty with lithium-ion battery, and I regularly connect with the experts, basically who are working in industry, and we help them in order to train on a given topic, and we also provide them the knowledge base, what they are required according to the customization that they request. At Skilling, I have been with the company for more than 5 years, and we take care of a wide range of topics in terms of providing the training to corporates, whether it is related to ICE to EV, talent transformation, so from internal combustion engine to EV, or whether it's related to battery pack assembly, or it's related to vehicle manufacturing, or we have a lot of clients from tier 1 suppliers as well. So thanks a lot for joining in. Let's get started with the agenda. So this is the agenda that we are going to focus on today. So first we'll understand what is happening in industry, right? So what are the lithium-ion chemistries commercially available and which are proven, right? And which are in pipeline. And we will also look at the overall development cycle of a lithium-ion cell, and we will look into the overall adoption, right? So after that, we'll be focusing more on cell cost and manufacturing aspects, and we'll also look into the recent advancements where we have the innovations in terms of the components, and we'll also look at the comparison among the chemistry. And today I will also show you one such price table, which will be interesting to look at what is a new benchmark at a cell level cost and what is happening at a pack level cost as well. So that's about the agenda. I wanted to keep this webinar interactive, so feel free to stop me anywhere and ask questions, and at the same time I will also ask questions to you as an audience in order to have a better understanding of the topics that I'm going to cover today. So here I'm showing a big picture. So let's say we take an electric car, that is point number 1. Uh, so this is a battery operated or fully battery operated vehicle, which is called as a battery electric vehicle. And number one is the vehicle and the utilization of a battery in terms of the automotive application, right? Number two, when you move from one to two, so we are looking at a battery pack level, right? So here, uh, the one is what we are talking at a vehicle level. So let's say this flat battery pack is uh, added to the bottom of the chassis, and it is electrically connected with the all high voltage supply system of the vehicle, and that's how the vehicle is powered, right? So the vehicle is operated from the battery, and that is our point number one of discussion today. Now if we zoom in, or if we dive deeper into the battery pack, so the battery pack will something look like this. So let's say, because the volume and the weight of a battery pack, right? So the battery packs are designed in such a way that they can be kept as much lower center of gravity as possible, and the uniform weight distribution, right? So here we are looking at the cross sectional view, right, of the lithium ion battery pack. Now battery pack is made up of multiple modules, right? So here number three is where we have multiple modules connected in series and parallel, right? Now the modules comprises of cells, right, which is number four. So this is number two, which is at a vehicle level or battery pack level. And from battery pack level, we are now moving to the module, right, which is a smaller group of cell. Battery pack is a larger group of cell. And then we have cell, which is point number four. Now, this is one of the photograph of a prismatic cell. And internally, the prismatic cell can be made up of uh, the stuff like this, right? So it is all about electrochemistry, right? And the last, but not the least, right? That is point number five, which is the manufacturing process, how cell came to existence, right? So first you need a material, and then you need to get into uh, let's say electrode manufacturing, and then a lot of processes like calendering, stacking, winding, and uh, adding the cell into the case, right? And then basically packaging and dispatch, right? So number five is where we have a cell manufacturing process. So these are five different stages that we are going to talk about and consider. So just make yourself comfortable while talking at for a lithium-ion battery, right? For an EV application, which level we are talking about, right? So if I say the cost of a battery pack, right, which is at a vehicle level, now that can be different. The cost of the raw material, right, that can be very, very different, right? So we are going to touch upon all the five different stages, right? Now, before we get into that, right? So any idea how many typical number of cells will be required in one vehicle, right? So let's say this is a Audi e-tron picture, right? And this is a photograph of a battery pack of Audi e-tron. How many number of cells do you think would comprise of, right, in the entire battery pack? So feel free to unmute or type your guess in the chat box. So feel free to have your guess, like 10 number of cells or 100 number of cells, 1000 number
Maybe
of cells, right?
more than 300.
Typically, uh, more than 100. Yes, you are right. So based on the capacity, right, of a battery pack, based on the cell capacity, right? So the total number of cells in one vehicle, right, are decided. So let me see if there are more responses in the chat box. Yes. So first, Bhupesh is asking for cell voltage, right? Uh, that depends on the kilowatt, right? And 300, 400 prismatic cells. Yes. So your guess are correct. So typically a battery pack consists of a large number of cells, right? Now, when I say large number of cells, how many exact number of cells, right? So if you belong to a mechanical engineering team or electrical electronics, or you are part of chemical engineers team, right? You need to understand this, which is a basic stuff, right? So if I show you the overall uh, arrangement of a battery pack, right? So it looks like this. So here, what you see, this is the overall idea, right, of a 114 kilowatt hour of a battery pack, right? So 114 kilowatt hour, it's basically the largest capacity of a battery pack in the premium car segment or luxury electric sports car segment, right? Now, this typical battery pack would have many number of modules, right? So now here you can see the photograph or the arrangement of modules which are connected with the high voltage wiring harness in the orange color, right? So typically one module has 12 number of prismatic cells, right? And this is how one module consists of, right? So apart from cells and the module, the battery pack weight and the battery pack cost involves the packaging material, right? It will also have a lot of other material, let's say the lower protection cover, right? The battery cooling or battery thermal management system over here, right? The frame of the battery which is connected to the chassis of the vehicle body, and you will also have a housing tray, right? And the aluminum structure which is going to hold the different modules which are shown over here. And along with that, you will also have something called as electronics, right? So there is a battery junction box, and there is a battery management controller, right? Which you can see here, BMC, battery management controller. And there will be a lot of different mechanical packaging materials, right? So the packaging material as well as the electronics and the wiring harness, right, will be added on the top of the cells, which are the raw material, and that's how the battery pack is constructed, right? Now, if you are an engineer and you are curious to know more about how many exact number of cells, right? So let me answer that question, right? So how can we get into that? So we need to get into the technical specification of a vehicle, right? So what are the technical specification of a vehicle that we have seen? It's a 114 kilowatt hour battery pack, right? And let me open the uh, whiteboard and show you how exactly the simple calculation can be done. So I hope the whiteboard is visible to you all, uh, where I will uh,
Yes, sir.
write. Yes. Okay. Thanks for confirmation. So here, let's consider the largest kind of a battery pack for EV application, right? So let's say we are expecting more than 500 kilometers kind of a range, right? And it's not a small car, right? It's not an entry level car. It's a premium segment car which has let's say 114 kilowatt hour of battery pack, right? So typically what we need to understand from the capacity, right? So it is as good as a capacity of a battery pack, right? Which is as good as the capacity of a water bottle, right? So this is the amount of thousands of watt hours the battery can store, right? So the battery is capable of storing this much of charge, right? So when the battery is fully charged, it is going to deliver, it is capable of delivering 114 units of electrical energy, right? So one unit is 1 kilowatt hour, right? So this is the overall pack level technical specification. Now we need to get into the engineering technical specifications, right? So some of you already pointed out we need to understand the voltage of a cell, right? And voltage of a system, right? And we need to understand the capacity, right? So what is the capacity and what is the voltage of a system? So for that, I will take you through the engineering specification or technical specification of a vehicle, right? So let's say the vehicle under consideration is basically this, right? The Audi e-tron 55 quattro, right? And for that, here we can see the overall real world range, the overall efficiency, right? And typically the range under various driving and environmental condition. And here you can see the battery specifications, right? So this is one of the website which has compiled all the vehicle technical specifications, right? So you will be able to get uh, majority of the vehicles, right? Let's say Volkswagen ID2 or let's say Dacia Spring, like mass market EV from Renault, right? Or you will also be able to get into the Tesla kind of vehicle technical specs as well, right? On evdatabase.org. So what I'm referring to is the nominal capacity of 114 kilowatt hour, and the chemistry of uh, the cathode material, right, is nickel, cobalt, aluminum, and the pack configuration is 108 number of cells in series and 4 number of cells in parallel, with the prismatic type of a form factor of a cell, and the voltage of a system, right, to be approximately 400 volt, right? So this is a 400 volt battery pack, which has total 432 number of cells, right, where each cell capacity is 72 ampere hour, right? So now you can figure out how this configuration will look like, right? So we have 108 series and 4 parallel as an overall configuration, and that's how the total number of cells are 432, and they are divided or distributed among various modules, right? So this is how the battery pack is constructed. Any doubt, any questions on whatever data I was sharing to you? Any questions? Okay, let me check if there are any question in the chat box. Yeah, so I think this is clear to all. So here, in terms of the pack configuration, right? So let me take this pack configuration in more detail and explain you how this works out, right? So typically, uh, we have 108 number of cells in series, right? So 108 number of cells are connected in series, so that's how it is 108s, right? And there are 4 cells which are connected in parallel, right? So this is the overall configuration. Now this is at a battery pack level. So now battery pack will have multiple modules within itself, and here let's say this is the overall battery pack, and it is divided into various modules, right? So here this is how you will have different modules, right? So let's say you divide the entire thing into 3 sections, right? So this is, let's say, module number 1, 2, 3, 4, 5, 6, and 9, 10, so on, right? So this is how the modules are stacked up together, right? So when the modules are stacked up together like this, that's how the entire battery pack is constructed, right? So depending on the capacity of the entire battery pack, depending on the capacity of the entire the cell which is selected for the design of this battery pack, you can figure out the total number of cells required, right? So here, if we just want to get the more idea about like 432 number of cells, right, which accounts for 114 kilowatt hour. So the amount of watt hour per cell we can figure out, right? So let's say I will use this calculator just for the clarity of understanding. So let's say 114 uh, kilowatt hours, right? Uh, divide by the number of cells, which are 432, right? So one cell consists of 263 watt hours, right? So now we might have a battery pack design where one cell watt hour or capacity can be as low as 30 watt hours, right? Or it can be 50 watt hours, right? Or it can be more than 250 watt hours per cell as well, right? So now from the data revealed by Audi, right, we know that the one cell capacity is 72 ampere hours, right? So I will just divide this watt hours per cell by ampere hours, right? So that I will get the value of the voltage per cell, right? So which gives me 3.66 as a nominal voltage, right? Because I know the ampere hour capacity per cell is this much, right? So now once you know the arrangement at a vehicle level, right? Let us dive deeper into the aspects, right? So where we were looking at the point 1, 2, 3, 4, 5, right? Now is the time to uh, go in the right direction, which is from 5, 4, 3, 2, 1, right? So why do I say that as a right direction? Because that's how the assembly, right? That's how the manufacturing happens, right? So from our understanding point of view and getting the idea of how things are assembled, how the things can be, right? We have got to know uh, the steps 1, 2, 3, 4, 5. But in order to do the design and manufacturing, we'll be following steps 5, 4, 3, 2, 1. So let me show you the arrangement of 5, 4, 3, 2, 1. And this is what we call it as a value chain, right, for electric vehicle batteries. So what is a value chain? So the first step, uh, right, comes as a component production. But before the component production, you will have something like a raw material production as well, right? So the raw material production is the first step, right, where you extract the material, right? So from where do we extract the material? Mines, right? So we'll have the mines, and we'll have a natural resources of the metals, right? So that's how we extract lithium from the lithium ore, or we extract iron from iron ore, right? And then we will have a component level production, right? So this component level production is basically the manufacturing of cathode and anode active materials, right? So typically they are called as a CAM or AAM, right? So the short name CAM stands for cathode active material. So now I have a red line and a blue line, and there is a separator and electrolyte which are not shown here for simplicity, but this gives you the clarity in terms of what goes inside the assembly of a cell, right? So depending on the chemistry, depending on the capacity of a cell, we require the component production companies, right? Or basically the raw material supplier company, right? So raw material supplier companies are going to provide it to the cell manufacturing company, right? So and there are various cell manufacturing companies, and there are many different companies who are raw material supplier companies, right? And there are processes and which needs to be followed in order to have a cell production, right? So what is a cell? It's a positive electrode, negative electrode separated by the separator. And then you have multiple cells which are connected together. Then you have module. For example, the module in the previous case was three series and four parallel, right? So there are 12 number of cells in each module, for example. So in that way, you have a module. Now multiple modules connected together, you have a battery pack, and multiple such modules, and the entire battery pack will be connected with the vehicle. So let's say it may be a smaller battery pack in the rear side of a vehicle, or for a full electric vehicle it can be spread across the body of a vehicle, right? And then comes the utilization, which means the battery pack is charged, discharged, and the vehicle is running in the field, right? So vehicle runs on a road for let's say uh, according to its life, and the use phase there is a degradation, right, which happens, and after that there will be a second life and the recycling, right? So there is something called as a reuse, first and then the recycling. So this is the overall value chain for electric vehicle batteries. Now I have a question here in the last two phases. So why do we have something called as reuse? Why it's not direct recycling? So what is the difference between reuse and recycling? So feel free to unmute and or feel free to type your response in the chat box.
Reuse means we can charge it again when it get discharged, and
Mhm.
recycle means once the life cycle that will complete, then we will go for the replacement of EV.
Right. So here, so there is a, I would like to add one more point, right? So there is something called as use and there is something called as reuse, right? So use is within the vehicle, right? And this is the first life, right? So we call it as a first life of a lithium-ion battery. The reuse, we also call it as a second life of a lithium-ion battery, which means the same cells, right, which are already been used in a battery pack where the vehicle owner may get it replaced, right? Or the vehicle is going to have end of life and the vehicle itself is going to have a scrap, right, scenario. Now, reuse means utilizing the cells, right, in a different application, right? So let's say the degradation of electric vehicle battery pack, right, happens in such a way that so let's say here I'm talking about the capacity on the y-axis and the number of cycles or life cycles on the x-axis, right? So as the number of cycles elapses, the capacity degrades, right, or capacity reduces. So let's say this is the by default capacity. Now the capacity reduces to some extent where um, it is significantly lower. And this is the time where the owner of the vehicle may replace a battery pack, right? So this is the time where more than 80 percentage capacity is still remaining, right? What does this mean? Electric vehicles are never going to consume the battery fully, right? So it is not the end of life, right, that will happen within the vehicle, right? So there is a second life usage, right, which is still there. Now, when I say this, right, what I said, electric vehicles are not going to consume or not going to utilize the battery life fully, right? Why, right? Why can't we have a vehicle which is utilizing the entire life of a battery pack, let's say like this, right? So let's say here we have maybe 2000 number of life cycles. Why can't we go ahead and have 5000 or 8000 number of life cycles, right? So what's the problem? Why EVs require a second life, or why do EV application of lithium ion battery has a reuse case? Can anyone throw some more light on this? Okay, I ask the question again. So why electric vehicle battery packs are replaced before they are completely degraded?
Range is going to be decrease, I can say. The cell capacity which is having maybe
Mhm.
going to decrease, I think so.
Great. So there is something called as a remaining useful life. We call it as a RUL, right? Which is going to be pending, right? So now, let's say initial period of time where the range of a vehicle is as high as, for example, 400 kilometers per charge, right? So now battery degrades and your range reduces to 350. Now the range reduces to 300, right? Now the range is, let's say, less than 300. Now this is the time where the user may not uh, find it convenient, right, to charge the battery again and again, right? Also there are constraints in terms of the charging and discharging power levels, right? So as the capacity degrades, the power level of discharge and the power level of charge remains the same. So we can't allow the battery pack to have same power levels with the degraded capacity, right? So it is always recommended that the battery pack has to be replaced without getting the complete juice out of a lithium-ion battery for EV, right? So the range reduction as well as the performance constraints, right, and frequent connect to the charging point, right, are the issues, and therefore the lithium-ion batteries will have something called as a remaining useful life, right, and hence there is a second life, right, which is required where we utilize the cell for the remaining number of cycles, right? What does this mean? So here, uh, this battery pack will be decomposed or deconstructed, right? And it can be used in a various application. It can be stationary energy storage system, or it can be, let's say, solar energy backup system, right? So it can be energy storage system at a power level, or it can be any other application where this cells or this modules can be reutilized, right? So once there is a reutilization, I will give you the one real world example. So let's say you have a toy car of your kid, right? And your kid is going to drive this remote control toy car, right, for let's say 2 weeks. Now after the 2 weeks, uh, the toy car cells, right, which can be AA or AAA type of cells, you all must have replaced it, right? There might be 3 or 4 or 6, right, depending on the type of a uh, remote control car, right? Now, once you replace these cells, it's not something that you can throw away, right? They are not completely discharged, right, or they are not completely utilized. Now, the same cells can be added into the wall clock, right? So let's say you have a wall clock which requires a little amount of power. So this wall clock, which requires a little amount of power, there the cells can be further used, right? So this is as good as reutilizing the cells, right, from a remote control toy car to your wall clock kind of an application. Now, exactly the same happens over here, and that's how the lithium batteries are going to be finally go to the recycling. So recycling is again where the important materials will be taken out from a cell, and that can be added to the step number 1 over here, right? So let's say whatever is the amount of mining, right, required here, right, uh, the active material from the recycling, right, that can be utilized at this stage, right? So this is how the circular economy or circular value chain of the electric vehicle batteries work. I will take a pause here if there are any questions, or if somebody from the participants is looking for more clarity on whatever I talked about. Okay, so assuming everybody is clear on this, let me.
Vatsal,
Yes.
there is one
Yes.
question on the chat window. Let me read it for you.
Sure.
How to estimate total number of cells based on voltage and capacity of each cells?
Great. So the total number of cells, right? So we have done a very simple exercise over here, right? So now because this data is known to us, right? So I was looking at a technical specification or engineering specification of this battery pack. That's how we know, right? Now the voltage, let's say high range kind of a vehicle, right? More than 250 kilometers of range can be obtained from such a battery pack. Where if I assume the nominal system voltage is 400 volt, right? I can get the capacity, right, which is usually declared in ampere hours, right? Just by dividing this with the voltage, right? So if I do this 50,000, right, divide by 400, now that gives me the ampere hours, right? So here, what typically we get, right, is uh, 200 amp hours, right? How? I will divide 50,000 by 400 volt, which is a system voltage. Now, why do we have 400 volt system? That is as per the electrical design, right? So if you
Hello, Vatsal. We are unable to hear you.
Yeah, I think Vatsal, yeah,
am
he's
I
back.
connected?
Yeah, you're reconnected.
Is my screen shared?
Yeah, it is visible.
There was some glitch in my network. So I hope I was clear up to this point. So I was talking about the assumption of 50 kilowatt hours with a 400 volt nominal voltage as a system. Now I have 125 ampere hour of battery capacity, right? So this is how typically the capacity is calculated. Now, number of cells, right? So let's say, how do we figure out the number of cells? So now that depends on a cell level specification. So whatever I talked about is a battery pack level specification. Now, the next thing that we need to consider is a cell level specification. So in order to construct this battery pack, what kind of a cell is?
That's it. Your audio is gone again.
Hi, Venkat, am I connected?
Yeah, you're connected.
Yeah, sorry for the disturbance in my internet connection again. I was discussing about the cell level technical specifications. So if I assume this, let's say battery pack technical specifications, which are 50 kilowatt hour, the system voltage is 400 volt. Now I got to know the capacity in ampere hours to be 125 ampere hours, right? Now, if my cell selection, right? So this is at a cell level now, right? Now, if the cell nominal voltage is to be 4 volt, right? Normally, the cell voltage, the real values are 3.2 volt, 3.3 volt, or 3.6 or 3.7 volt, right? But if I assume 1 volt, one cell nominal voltage is 4 volt, and its capacity is 12.5 ampere hours, right? So let's say one cell is of this much specification. Now, in order to go from 4 volt to 400 volt, I need to connect 100 number of cells in series, so which gives me 100 series requirements. And in order to go from one cell of 12.5 to total capacity of 125, right, will require 10 number of cells to be connected in parallel, right? Now, this is where the total number of cells, right, will be 100 series, 10 parallel, 1000 number of cells, right? So this is how the number of cells are calculated, right? So now instead of this, I have one cell itself of let's say the full capacity 125 ampere hour capacity, one large cell, right? Now we'll require only 100 number of cells, right? So we'll require 100 series and one parallel kind of a configuration. That means we require only 100 cells, right? So depending on the capacity per cell, will require either 1000 cells or will require 100 cells, right? So that's how the simple calculation looks like, right? I hope I answered the question in the chat box. If there are any follow-up question, please ask. So now in order to, for you to understand this, I added simple battery terminologies over here, right? So battery watt hours are basically the nominal voltage times ampere hours, right? And that's what is a formula I applied, and that's how we calculated, right? So I'm assuming there are no follow-up questions. So there are a couple of other terminologies which I will be using. State of charge is the battery percentage level which is pending, right, to be discharged. The depth of discharge is the battery percentage level which is already discharged, right? So and the state of health is nothing but the capacity, remaining capacity of a battery after the significant cycles have elapsed, right? And C rate stands for the current rate, and the current rate at which you are charging or discharging the battery, right? That's what is typically called as a C rate of a battery. So these are the frequently used terminologies from which you can know more about the batteries. So let us now get into the uh, notable industry events, right? And sorry, before that, let us understand the technical terminologies of what cells are comprised of, right? So cells can be the metal oxide, right? It can be with cobalt, aluminum, manganese, right? So the lithium cobalt oxide, nickel cobalt aluminum, or nickel manganese cobalt, right? These are very popular metal oxide uh, chemistries, right, which are used in the cathode material, right? So what exactly we are talking about? What is the type of material used in the cathode, which is highlighted here in the pink color, right? So this cathode material, based on that, there are classification of cell chemistry. Now, based on that, the cell chemistries are classified into metal oxide, olivines, or spinels. So, lithium iron phosphate is a spinel type of a structure, what you can see over here. And lithium manganese oxide, lithium titanium oxides are basically the olivine type of a crystalline structure. So this is what is used in cathode, right, for lithium ion batteries. The anode material is usually the graphite and the hard carbon, right? And typically it's a carbon based low cost material, right, which is the anode material, right? So typically what we call anode as a negative electrode, cathode as a positive electrode, right? So what lithium ion cell consists of? It is basically the current collector for both the electrodes. So let's say the copper current collector for anode, the aluminum current collector for cathode, and then there is a separator, right? So there is a separator which isolates electrically the anode and cathode internally from a cell, and then we have a structure, right, or the electrolyte, right? So the entire cell is immersed into the electrolyte. So electrolyte is a material which is going to allow the ions to pass through it, right? And the separator will also allow the lithium ions, right, to pass through it. So the electrons will not be to flow inside the cell, only the ions will be flowing. Yes, anyone, any question? Any questions from anyone? Okay, I'm assuming no. So what happens when we charge and discharge the battery, right? So let me show you one simple animation on how exactly the charge and discharge happens, right? So let me play this, right? So what is happening? Let's say you have a vehicle and you are discharging, right? So basically, uh, the electrons are going to flow from here to here, right? Or when we can say the current flows from the positive red wire to the negative black wire, right? And that's where you have a vehicle as a load connected, right? And the electrons will flow in the reverse direction of the current, right? The lithium ions are going to flow from left, from I will say uh, right to the left, right? So right to left is the mobility of the ions, right? And that's where that's how the discharge occurs, right? So this is what happens inside a cell, and that's how the cell is capable of delivering electrical power to the external electrical network. So now what happens when you plug in the vehicle, right? So let's say this is how all lithium ions have migrated from the left side, sorry, the right side to the left side. Now, when you have all these ions over here, that this is the condition which is fully discharged condition, right? Now, once you reach here, you are not recommended to discharge the cell further, right? So let's say your cell is in the low discharge condition. Now you will plug in the uh, charger, right? So when you connect an external charger, the direction of ions and the electrons will reverse. And now you can see the electrons flowing from the red wire to the black, right? And this is where the vehicle is connected to the charger. And this is where now the ions are moving from left to right, right? So this is what happens when you charge, and this is what happens when you discharge. So now you have the lithium ions which are passing through this separator, right, are now getting accumulated, right, on this electrode, right? So this is what happens when you charge and discharge the battery, right? So this animation will help you to understand this is what is discharge, right? So where the lithium ions are moving from the right to left, and when you charge, the lithium ions are moving from the left to right. Yeah. So this is the overall arrangement and what happens inside a cell, right? So now let's deep dive and understand more about what kind of cell chemistries are commercially available and what is a typical pricing level, right? So we will now start talking about the type of materials and the price levels as well. So this is a lithium ion chemistry spider graph comparison. So these are the 6 popular chemistry which are existing. So when I say popular, these are all commercially available lithium ion chemistry, and they have been existing from in the market from many years from now, right? And this is where if you compare, right? So the higher the area in the blue color, uh, higher are the chances of getting it deploying for the EV application, right? Or better the performance of a battery, right? So here, the lithium cobalt oxide, manganese oxide, and nickel cobalt aluminum, right? They have slightly lesser coverage area compared to the lithium iron phosphate and nickel manganese cobalt. So nickel manganese cobalt and LFP, right? Lithium iron phosphate, lithium ferrous phosphate are basically the 2 chemistries which are under consideration for EV application. There are a couple of vehicles, just like the Audi uh, e-tron, right? That type of architecture, or some of the vehicle in Tesla earlier also used nickel, cobalt, aluminum kind of a chemistry as well, right? So that these are 3 popular chemistry now, which is more becoming popular is NMC and LFP, right? So let's compare them together and let us understand more about this too. So lithium titanium oxide is also one such popular chemistry, but this is very, very costly, right? So as you can see on a 4-point scale, it has got just 1 out of 4, right? Which means very, very costly. Lithium iron phosphate 3 out of 4, which is relatively cheaper. The nickel manganese cobalt is also 3 out of 4, right? Is in general or a very generic comparison. Now we are going to do very specific comparison and we'll understand more details about how the cell level cost will look like, right? So let us compare the third one and the fourth one, because now they are strong contender, or they are more deployed for the EV application. So here you can see specific energy is higher. Lithium iron phosphate will be heavier. The specific energy is lower. On the other side, the specific power or the C rates, charging and discharging rates, are typically higher. It is more safe, higher operating temperature margins. The overall performance is also 3 out of 4. And then the life cycles are more, right? And because now this type of cells are in large volume production, their costs are also very, very effective. So this is not the fair comparison 3 out of 4, 3 out of 4 for both, right? We need to be uh, considering a lot of different factors in order to distinguish between this 3 and this 3 as a pointer. So typically, if we compare this two, we will get to know how the cost at cell levels are uh, there, right? So I am curious to know how many of you are aware of what is the per kilowatt hour price of a lithium ion cell. So can you type your answer in the chat box? So I want all of you to uh, tell or suggest your guess, right? Or feel free to have your guess in the chat box. 1 kilowatt hour in US dollars, right? So that is the international market price. That's how we consider. What is the current price level of 1 kilowatt hour in US dollars, right? At a cell level, right? So I will take a pause here and then we'll understand your guess, and then we'll discuss the next points. So let me check out the chat box. Okay, $120 per kilowatt hour. Ashwini Mishra. Chinmay says $115. Okay, interesting. Anyone else? So what are the current cell level cost? So the cell level costing is basically very dynamic thing, and so whatever we are talking about is a volume weighted average price, right? Among different chemistries, among various suppliers, right? So it is as good as what is the temperature in India today, right? So you can't really uh, give a very accurate answer unless and until you know latitude, longitude, and unless and until you know the day, time of a day and the day of a season, right? Now you know you need to know a lot of parameters in order to comment on that, right? So we'll look into what are the parameters that affect the cost, but I will show you the real price levels. To your surprise, this values, right, are way less than whatever all you have commented, right? So I will show you the real prices that are existing in the market right now. Okay, so let's go back to the chemistry comparison. So yes, someone rightly pointed out it depends on the chemistry, it depends on the quality of a cell, it depends on the supplier, it depends on a grade of a cell, right? It depends on the volume of trade, right? So how many number of cells you are ready to buy, right? So with all that, the price fluctuates, but we'll look into all these factors later on. So if we compare these three major chemistries which are existing in the market, right? So typically their specific energy are of the order of 220 watt hours per kilogram. NCA is relatively up to 250 watt hours per kilogram. So these are typical numbers. So lithium iron phosphate have slightly lower voltage levels, right, and higher weight, and that's where their kilograms are higher, right? So these battery packs are heavier. Now, what will be the problem with a heavier battery pack for an electric vehicle? So if the weight of a battery pack is higher, what is the challenge? So according to you, as an engineer, if the weight of a battery pack is higher, what is the challenge in that, right? So if this number is around 100, uh, is this challenging? So the weight of a lithium iron phosphate type battery will be higher for a same capacity. Now, uh, yes, let me see if anybody is able to reply this question. Less range. Yes, performance and the range. Thanks, MR Kannan and Senthil Kumar for answering that. I agree with you. So what happens basically if your battery pack is heavier, right? So here in this case, so let's say this battery pack is going to weigh around 500 kilograms, right? This is just a guess, right? So now typically the 114 kilowatt hour kind of a battery pack would be somewhere near to 500 kilograms minimum, right? Now based on that, the 500 kilograms, right? Now the amount of effort required to move the vehicle, right, or the amount of energy required to carry the battery itself, right, is more. So now if I have a vehicle which has 400 kilograms of battery pack with same capacity, and I have 500 kilograms of battery pack with same capacity, I need 100 kilograms of more effort in order to basically uh, help the battery to move along with the vehicle, right? So the effort required to carry the weight of a battery itself is a bottleneck, right? So for an EV application, the lighter weight battery pack would be more desirable, right? So the lighter weight battery pack are basically where they have a higher energy density, right? So NMC and NCA have typically higher energy density, and they are still popular, right? So these are some electrical technical specification. I will not get into that part, but if you see the number of life cycle, LFP have 2000 and more. Typically, way more higher than these two different chemistries, right? The temperature, the decomposition temperature, or the thermal runaway, the internal cell temperature at which the cell is going to explode, right? So it is much more beyond the operating temperature, right, which is 270. So you have a higher safety margin. Uh, NCA is typically 200, right? 150 to 200, depending on the chemistry, and NMC has 210 degrees centigrade, right? So LFP has better life cycle and higher safety, and hence all automakers, all battery manufacturers are attracted towards that, right? So now if you compare this to, you will feel like, why can't we have a combination of these two, right? Why can't we combine the higher energy density with the better life cycle and the safety over here? Now, yes, that is possible. We'll look into that kind of a chemistry later on. So these are the type of chemistry, and this is what is a trend, right? So this graph typically shows how exactly uh, the percentage penetration, right? In China, right, in all the electric vehicles from the year 2016 to 2020, which type of chemistry of the battery was more popular. So 2016, it was LFP, lithium iron phosphate, which was more than 70 percentage. In the last couple of years, NMC become very popular, and in 2019, it was having a market share of around 65 percentage. But now the trend is where the NMC deployments are lesser and LFP has more adoptions, right? So higher and higher EV automakers are going with the choice of lithium iron phosphate. So this is the overall trend, right? So now they are going almost neck to neck, right? And there are various options also available under the NMC chemistry, right? So the nickel, manganese, cobalt has typically the three options, right? So various types of NMC depending on the amount of nickel, manganese, and cobalt used, right? So if it is NMC 111, which means all these three components are equal. So 33.3 percentage nickel, 33.3 manganese, and the same percentage of cobalt. So this is what we call it as NMC 111, right? Now, in order to be independent of a cobalt supply and be independent of the cost controlled by the mining of the cobalt, right? There are chemistries which are now becoming popular, which is NMC 811. So 80% is nickel, 10% is manganese, and cobalt is the another 10%, right? So that's how NMC 811 is more popular chemistry, and that's how the notation is there. So now this does not mean the weight of the entire cell, right, of NMC 811 is due to only three of these components, right? So these are the three components of the cathode active material which we are talking about, right? So it's not completely the entire cell or the cost of the entire cell, right? So the entire cell would consist of a lot of different materials, right? So this is just the classification of the cathode active material of a cell, which is in the proportionate of 811, right? So I hope you got this point. Now, what are the cell cost uh, basically comprises of, right? So now, if you know, like you go with a luxury electric sports car like this, right? Uh, what percentage of the cost of the vehicle will be the cost of battery? Can anyone comment in the chat box? So what percentage of cost of vehicle will be the cost of a battery pack? So this can be again a tentative number, right? So depending on the overall understanding, right? So what can be the guess? So in a large battery pack vehicle like this, right? So here what exactly we'll have is it will have a larger percentage, right? And if you consider a small car like Morris Garage Comet, right? So which has less than 20 kilowatt hour battery pack, probably that cost in terms of percentage of vehicle will be lower. But somewhere, let me see if anybody has the correct guess. 50%, 40%, 60. Yes. So 40 to 60% can be the range of the cost of a EV battery pack inside the vehicle. So getting into that, what is that cost of a cell, right? So now in the bill of material of a vehicle, if 40 percentage or more than 40 percentage cost is of a large battery pack, what is the cell level cost breakup, right? So the first in the entire cell level cost breakup, more than 50 percentage of a cell cost is due to the cathode active material, right? And this is where the price of the lithium ion cells are driven by the cathode active material. So the lithium iron phosphate and the nickel manganese cobalt, they all depend on the lithium and the nickel manganese cobalt etc price and the raw material pricing. The manufacturing and depreciation is another 24%. The anode only cost around 12% of the total cost of a cell. The separator and electrolyte are 7 and 4% respectively, and the housing or a casing material, right, or a body of a cell, that is around 3% cost, right? So this is the cell level cost breakdown. And if you are interested to study further, right, and understand more about the dynamics of cell level costing, I will suggest you to go and check out the standard report that are published every year, right? So let's say the Volta Foundation is one such non-profit company. They publish the report, right? And I'm going to show you the glimpse of uh, the couple of cell level cost breakup, right, from this report of the year 2023. So they have produced reports every year. 2020 onwards, they have every year they have a report. And if you look at the data represented, right? So I hope the screen is visible with this report in the full screen mode. Is this visible to you all? I'm assuming yes. So,
Yes,
so NMC 811 typically, uh, let's say, I will go back, right, which is uh, one of the cheapest comparison with LFP, right? So their cost, right, in the year 2023, right, was this, right? So initially in the month of January, this was the cost. Now, where we are at the end of the year, right? So the cell level cost have been drastically reduced, right? So we'll look into that details as well. So what is happening? The raw material prices are basically uh, declining. So $65 per kilowatt hour um, is the current trigger level, right? So if the costs are below that, right, so then it is possible to go at less than 100 US dollar per kilowatt hour at a pack level, right? And that will further make the EV game interesting, or I will say more competitive to the internal combustion engine market, right? So these are the tentative pricing, right, when it comes to the raw material, the labor, and the processing or the manufacturing of a cell, right? So these are the cost level tentatively. So here, if you look at uh, the NMC 811 cost split, right? So the cost split among the various chemicals like lithium hydroxide, cobalt sulfate, nickel sulfate, manganese sulfate, and the graphite, how much percentage they share right now, and what can be the future, right? That is also indicated over here. So this is one such consideration, right? And here you can see the cell level and pack level cost. Some of you already said the year 2023, $100 per kilowatt hour. The year 2024 and the new benchmark price is what I will show you uh, now. Yeah. So this is one such popular report, and as an engineer or as a manager or as a person who is going to be involved in decision making related to EV batteries, you should definitely follow the Volta Foundation report. Now, with that, I will come back to whatever we were discussing, right? And in terms of uh, typically how the spread of a market looks like, right? So let's say CATL has more than now 40% of the market share. So this is the company based out of China. BYD is now second. The LG Energy Solution, or formerly the LG Cam, is third, followed by Panasonic, SK Innovations, Samsung, and then all other small players, right? So majorly dominated by China, more than 60%, and then Korea and the Japan, right, are basically the um, source of cell manufacturing companies, or where they are located at, right? So uh, if I talk about the costing part a bit more in detail, right? So this is what I got as a cost sheet from a Chinese reseller, right? So basically, they are not cell manufacturers; they are traders, right? So they are trading the cells, right, from the various manufacturers. Now, here, if you look at the price levels, right? So the price levels are varying based on the uh, minimum ordering quantity, right? So here, if you look at the minimum ordering quantity as per the pallet or the standard packaging that they have, so you need to order minimum 1,80,000 number of cells, which are of A grade or better quality cells. Now, from the supplier like EVE, right, which is a popular supplier, where they have a cylindrical 21700 type of a cell, uh, in the different payment method, right? Whether LC or OA or cash, right? X work Shenzhen, where you need to afford for the shipping and the tax part, etc. Per cell cost is around 1.5 US dollar, right? So this is the current cost levels, right? If you consider this much of volume, right? Now, from this, let us calculate for 1 kilowatt hour how much exact US dollars, right, will be there. Now, how do I calculate US dollar per kilowatt hour? So let's say I take one more cylindrical cell as a reference from the Goshen, and I consider the most attractive payment option, right, where the per cell price is $2. Now, in $2, what do you get is 3.2 volt, 15 ampere hour cell, right? So let us calculate how much is going to be the cost, right? So 3.2 multiplied with 15 ampere hours, right? This is going to give me 48 watt hours, right? Now, 48 watt hours are available in $2, right? So which means in US dollar per kilowatt hour. So this is 2 divided by 48, right? Multiply by 1000 in order to match the unit of kilowatt hours. So let's say if I multiply this, so 41 US dollar per kilowatt hour is a cell level pricing right now, right? So this is the November latest price that I received, right? And this is near to $40 per kilowatt hour at a reseller level, which means if I directly go to the supplier, right, and if I go for a bulk deal, right, or a higher volume than the 50,000 number of cells, the prices can be even better, right? Or the agreement can happen at much more less than $2 as well. So the current benchmark, right, at cell level cost is typically less than $50, right? Now that's what is very, very attractive to all the battery manufacturers, as well as uh, the all other applications which involves lithium-ion battery, right? So this is what we have seen as a current cost levels, right now. Less than $50 1 kilowatt hour is a benchmark which is already now broken, right? Where let's say the cell level and the pack level cost, right, are typically in the ratio of 1:5, right? So now you just need to add 20% extra cost of electronics and packaging. Now that is also becoming cheaper because of various number of suppliers. So if you go to $50 over here, right? Now your pack level cost in 2024 is somewhere around $100 per kilowatt hour, and that is the next level of trigger that we have observed this year, right? Because of large demand and the larger capacity of supply as well. So if you have looked at 2020 onwards, the trend was almost flat, right? But now we have got that trigger down in the year, in this year 2024, where the batteries have become better and more affordable, right? So I hope this is clear to everyone, and let us move on next to get the idea of how the battery packs are basically uh, considered in terms of the recent advancements, right? So what are the recent advancements? So as I said, instead of NMC and LFP, and then they are both uh, better in their own perspectives, right? Why can't we have something which is combination of the two? So people have already tried it. So there is a chemistry which is called as lithium manganese iron phosphate, which is not using any cobalt. So it's a cobalt free battery, and it has combination of both, right? And it is going to offer the advantage of both chemistries as well. So this is typically at a I will say pilot level, but many companies have started producing samples, and people have deployed them in their test vehicle, in their test battery pack, and so far the feedback, right, from this is coming good. So there might be a slight movement, right, in terms of LMFP as well, right? So which is a new chemistry. So LMFP typically offers around 200 to 240 watt hours per kilogram, where your vehicle battery range can be this much. And there are companies like Ferrasis, CLB, Goshen. They have indicated like they have already launched their sample cells, right? And then the trials are happening now, right? So this is the overall comparison. So in terms of NMC, this is a green area in the spider graph, and LFP, which is a blue. Now LMFP is something in orange, which is definitely going to be the wider coverage, right? And better energy density and better operating voltages. That's what we can expect from a new chemistry. So there are different other advancements happening where people have started using graphene. So the graphene batteries are going to be typically the lightweight and more durable, and it is going to provide 30% more power, right? So let's say the company like Yadia, which is a popular Chinese electric two-wheeler manufacturer, they have started using graphene in the lithium-ion batteries that they have used. Now, there are other chemistries basically which are going in the cobalt-free direction. So Tesla has also initiated their announcement of Gigafactory and all that, where they will not be dependent on cobalt, right? And that's where lithium iron phosphate is basically now the very popular cell chemistry. Sodium ion batteries are also in place, right? So I will say they are not in the lab now. So they are not just limited to the chemical engineers or the chemist, right, who are going to prepare the recipe in the lab and test their cell in the lab. So now the cells are available commercially for initial pilot project. So this sodium ion cells are also um, going to be one such better option compared to the lithium ion. However, they are yet to prove their performance. So when we can say lithium ion batteries, they are more than 15 years old. The sodium ion batteries, according to their cost and the performance, they are yet to prove themselves, right? So and this is going to be one such new direction in which the developments have started happening. Solid state batteries, where the electrolyte material is not uh, liquid, right? It's solid, which will further add a lot of energy density, right? And it can lead to a higher safety, and it will lead to a higher number of life cycle as well. But so far, these advancements have stuck, right? Or it's not yet commercialized. So there are very few samples or very few manufacturers coming up with the actual solid state batteries. So these are some of the advancements, and there are other techniques, right, where people are working on, let's say, instead of cell to module and module to pack, now they have cell to pack, right, where there is a significant reduction in the weight of a battery pack and the way battery pack is assembled and manufactured. So this is also one of the recent innovation that has come up. So I will take a pause here, and if there are any questions or doubts related to whatever topics we have discussed in today's webinar, feel free to ask your questions. So the last 10 minutes for today's webinar, we will leave it to the question and answer session. So Venkat, let me know if there are any pending question in the chat box. So that's where we are at the end of the overall webinar. So
Thank you.
feel
Thank
free
you,
to
Vatsal.
ask your doubts or questions in case you want to understand anything related to the topics that I covered today.
Thank you, Vatsal. There are no questions as of the moment. Folks, please kindly share your questions. Mic is available for you. You can choose to unmute and ask the questions or post it on the chat window. The deck will not be shared. We'll share the recording of the session. We have also posted a feedback form on the chat window. Kindly take a couple of minutes to fill it up. We'll make sure to share the recording with you. As Mr. Vatsal said, let's spend the next 10 minutes on an interactive Q&A.
Yeah, thanks, Venkat. So while we are waiting for questions from the participants, I would like to take you through the notable events, right, which is compiled by the Volta Foundation report in 2023, right? So there are a lot of different announcements, right, that has happened, and it's shared month-wise, right? So here you can see the company like CATL, what Volkswagen is planning to do, right? What is the announcement from Tesla in the month of January, right? LG Energy Solution, CATL. So they have various announcements, and typically the small companies also, the startup like the startup or the chemical suppliers like Posco Chemical, right? What they are planning and what are their future roadmaps, right, that are being shared in the news articles over here. So these are all entire year's news article compiled into month-on-month announcements, right? So you will be able to see the announcements here, right? So the company like Stellantis, right, and or let's say the Tata Group is going to announce, or they have announced in the first week of June that they will have a $1.6 billion EV battery plant, right? And that's where the Agratas, if you have heard of, right? So they have started their operations in UK and India, and they are soon going to come up with their cell manufacturing facilities. So that's what are the announcements, right? And typically, if you look at what are the announcements from Hyundai, General Motors, right? And the companies Proterra, right? And later this year, Northvolt also filed bankruptcy, right? So those news are also captured here, right? You can check them out. So this is a very exhaustive report, I will say, and this will give you a lot of insights into uh, the battery world, right, and what's happening around. So far, the key takeaways: there are various chemistries, there are various types of cells in the EV battery pack, and the price levels have broken the record of $50 per kilowatt hour in the international market with uh, the minimum order quantities I shared, right? So this is what is the current price sheet, right, from a reseller. And if you like connect with a direct supplier or higher volumes, the price levels can be further attractive. Yeah. So these are the takeaway from today. And yeah, let me see if there are any pending questions. Ashwini Mishra is asking, do you have slides on DFMEA, testing and homologation of battery? So, Ashwini, basically, uh, in this webinar, that was not part of the agenda. I didn't cap those slide and learning material over here, but yeah, yes, we can definitely help you in order to understand more about the testing, right? So the cell level testing, module level testing, and battery pack level testing, and the failure reports, right? So those we can customize according to your training requirements, and we can have a direct discussion with you related to that. If you have any questions related to, let's say, the standards, for example, what US, Europe, and other people are following, or let's say in India, we need to comply with EIS 156, those are the things I can definitely share more details on. So, Bala, yes, the Volta Foundation report, you will be able to find it. You can go and subscribe. You will be able to get it for 2023. Yeah.
So you have shown last slide cell to pack technology.
Yes.
When the cells are directly attached to the pack instead of modular structure.
Correct.
How do they go about the cool? Because when it is a modules comprising of cells, there is a organized way of cooling channels. So when it is cell to pack, how do they organize the cooling channels?
Yes, so it will be entirely different thermal management system, Tanuja. So what happens basically, you will have, let's say, let me reshare my screen. So
Considering it is active cooling.
yes, it will be active cooling.
Yeah.
So I'm going to show you the cell to pack arrangement. So yeah, so this is how cell to pack arrangement will look like.
Yes.
Right now, when you have multiple cells over here, right? I hope my screen is visible to you.
Yes.
So here, what you see in the bottom, right? There you have a cooling channels, right? So it will be something similar to what you will have it in terms of modules, but because now there is no lot of material, right? So we are able to avoid a lot of material in packaging, right? So therefore, the cooling system can be more simplified, and the assembly process is also going to be more simplified, right? So here, what you are able to see is the cooling from the bottom channels, right? And that's how the coolant will be circulated. So if you look at the cylindrical cells, it will be the similar serpent type of a coolant channel passing through the surface of a cylinder, which is like you might have seen in the module level, right? So that the same can be used at a pack level also, right? So That's how cell to pack technology thermal management system look like. So let me see if I can show you a couple of photographs, right, of cell to pack. So yeah.
Because when we did the study of the cooling channels, what we found is the bottom as well as top coolant circulation is required. Otherwise, the temperature was increasing.
Sorry, can you speak louder?
Hello?
Yeah. Can you speak louder? What was your
During
question?
during our simulation study, what we observed, if the cooling channels are not on both sides, top as well as bottom, the temperature of the cells were increasing, and because of that, if there was any imbalance, that was giving trouble. Because after all, the
Right.
final aim is there should be no cell imbalance, like during the charging, and then
Yes. So
temperature should remain within
correct,
limit.
correct. So typically, I will say um when you consider the smaller form factor, right? So you need to have more aggressive cooling system, right? So
Yes.
basically, uh, when we consider let's say the material which is less, right, and we want to pack it in a lesser weight and a better form factor, lesser volume, then we will require to arrange them in terms of uh, the maximum amount of heat extraction, right? That we need to consider, right? So for that,
Mhm.
you might have a different cooling strategy, right? And you might have a
Yes.
different arrangement. So that that should be considered.
Mhm. But in general, what is the trend nowadays? The batteries which are coming, battery pack, they are having
Mhm.
only single side cooling channels.
For cylindrical cells, yes, the answer is correct. So there will be uh, cooling channel from either of the side, right? And that's how
Okay.
you can optimize the amount of cooling material, etc. Used, right? Yeah.
Mhm. Okay. Thank you.
The cooling arrangement for prismatic cell. Yes, Ashwini. Let me see if I can show you that. Just wait for a minute. I have the arrangement of cells. Just hold on. Let me see. I can bring it that now. So typically the prismatic cells will have a cooling plate in the bottom, right? And there you will have an arrangement, right, where uh, the coolant is circulated inside, right? And uh, the heat is extracted from the bottom, right? So that's how typically the cooling system will look like. So let me show you one such arrangement in a video. So just a minute, I will share my screen.
Uh, Vatsal, what if we are going to meet with some accident, if some
Mhm.
battery blasted inside? Like, is there any mechanism to avoid that?
Yes, so there are
Anyhow, yeah.
various levels of protection which are available. So basically, so whenever you meet a crash, right? So
Yeah.
one thing is the structural stability and the structural strength, right? And once you get the idea of like the impact, right? Then the next thing is to avoid any further accident, right, due to the electrical short circuit. So under the event of a crash, so there are crash detection sensors, and at a electrical power network level, there are arrangements like a pyro fuse, right, which is now mandatory. So the pyro fuse is something which will break your high voltage bus bar, and under the event of accident, if anything goes wrong, right, or any contactor is not functioning, right, or if you have, even if the fuse is operated, you might end up in a short circuit, right? So your high voltage will be disengaged, or high voltage will be de-energized with the help of something called as a pyro fuse. So that kind of protection features are available. So I will just share my screen in order to explain the cooling for a prismatic cell. Is my screen visible?
Yes.
Yeah. So here, what you can see, this is the arrangement, right, of how the things will look in a prismatic cell assembly. So here, this is a cell to module and module to pack. So here you have a cooling system, and there are cooling hoses, right? And there is a coolant which is circulated, right? So this is how typically the arrangement will look like, right? So let me go there and show you the actual system at a battery pack level, right? So let's say the battery modules are uh, added into the aluminum alloy kind of a tray, right, which is in the bottom. And now on that, there is a cooling system installed, right? So what you are able to see over here is a coolant hoses, cold plate, right? And there is a thermal pad. So the cold plates are basically the one which you are able to see in the pink color, right? And the thermal pad, uh, yeah, so this is what is the thermal pad in the pink color. This is where the heat is extracted from the cell modules, which are on the top of this area. And inside this, there is a cold plate, which you can see here in the zigzag format, right? So this zigzag format cold plate will be the uh, structure inside this bottom plate, right? So and that's where the coolant is circulated, right? So how the coolant is circulated from the inlet and the outlet in the black color pipes which are going and coming over here, right? So this is how uh, let's say this entire battery pack is divided into three sections. So first section, inlet and outlet; second section, inlet and outlet; and third section, inlet and outlet. And now they are combined into the total uh, entire battery pack coolant circulation inlet outlet, like that. And internally there will be a zigzag kind of a channel where the coolant will be circulated. So that's how the design of a cold plate, right, and a cooling system for a prismatic type of cell will look like, right? So I hope you are clear on the cooling system arrangement. If there are any doubts, feel free to ask. Um, so Anupama says passive cooling. No. So typically for a four-wheeler high voltage battery pack, majority of the vehicle manufacturers will have an active cooling system. So very few vehicle manufacturers are going with a natural cool system or passive cooling system. So passive cooling system will be for a smaller battery pack, let's say less than 5 kilowatt hour or around 10 kilowatt hour for two-wheeler and three-wheeler. Yes, that is correct. So thanks a lot, guys, for asking questions. And yeah, so it was really uh, a good experience to interact with you all participants today. And yeah, thank you very much. Over to you, Venkat.
Thank you, Vatsal.
Thank you.
Thank you all participants. I shared the feedback form again on the chat window. Kindly take a couple of minutes and fill it up. I'll close the meeting in a couple of minutes. Thanks, Vatsal.
Yeah, thanks. Thank you, Venkat, for hosting this webinar. Yeah, thank you all.